Welcome to section 6.3, Natural, Exponential, and Logarithmic Functions. In this section we're going to be looking at a very specific exponential function and logarithmic function with one particular base. In previous classes you've probably seen the number pi expressed as 3.14159 and so on. This number is non-terminating and does not have a repeating pattern in the decimal side. There's another number which occurs frequently in many branches of mathematics, and we use the letter E to represent it. This number is approximately 2.71828, 1, and so on. Similar to pi, this number E is also non-terminating and does not fall into a repeating pattern in the decimal. This number is also referred to as Euler's number, E-U-L-E-R, named for the Swiss mathematician Leonhard Euler. You can find this number, if you need it, on your calculator. You can also find pi by hitting the second button and then the division button. Pi is located just above this, under second and the caret symbol. So let's take a moment and figure out what is 1 over this number, E. Well, if I type 1 over that number into my calculator, I arrive at approximately 0.36787944, and so on. Similarly, we could calculate the value of E squared by typing E and raising it to the second power. I find that this is approximately 7.389056.1 if we want to round to 7 decimal places. Now this number is used so frequently in branches of mathematics that there are exponential and logarithmic functions where we use E as the base. The natural exponential function is exactly what you would imagine. It is a exponential function whose base is E. Now we know that this number E is approximately 2.718. Well, we won't carry the decimal approximation out any further than that. Since this is the case, since E is greater than 1, we can tell that this function f of x, the natural exponential function, will always increase over its whole domain. And it will have many of the, or all of the same features as any other exponential function with a base greater than 1. We know these types of functions have a y-intercept, and in fact we know that y-intercept will be the point 0, 1. We know that since these functions are always increasing, that they are also one-to-one. In other words, they are invertible. We know that these functions have a domain of all real numbers. negative infinity to infinity, and a range from 0 to infinity, not including 0. Just like 2 to the x, or 5 to the x, or 10 to the x, this function e to the x will have a horizontal asymptote, and it will be the left-hand side of the x-axis, since this function is increasing. We would describe that horizontal asymptote as y equals 0, the horizontal line at a height of 0. And just as is the case with every other exponential function, this function, unless it's shifted in some way, will have no x-intercepts. This is not something we've stressed in the past, but if I wanted to arrive at an accurate graph of this function, it would also be worth noting that this function contains the point 1e. In other words, if we input an x value of 1, we would get e to the first, which is e. And again, that's approximately 2.718. So we can force our function, when we go to graph this, to pass through this y-intercept and this point 1, e, and we'll demonstrate that it has a horizontal asymptote, and we'll make sure that our function does not cross the x-axis once we're ready to graph. So, if I draw out my axes, I'll label a few tick marks. Let's say 1, 2, 3, -1. So, remember our y-intercept will be at 0, 1. We'll also pass through the point 1, e. So if I come over to 1 and rise 1 to approximately 2.7, my guess doesn't have to be perfect, just as close as we can get, then I can begin to graph my function, maintaining that familiar shape that we've seen all exponential functions exhibit. On the other hand, we also know a significant amount about logarithm functions and their graphs. And with a base of e, a logarithm with that base would be called the natural log. Now, as with log base 10, this logarithm is used so frequently that it has its own special notation. This is often almost exclusively shortened and written as ln rather than log base e. So in the wild, if you encounter this function, this ln, what that means is the logarithm with a base of e. Now we'll recall from section 6.2 that since the base e is, again, greater than 1, we know quite a lot about the graph of this function, ln. This function will be increasing, In other words, it will be 1 to 1, and therefore invertible. It will contain an x-intercept at 1, 0. It will have a domain from 0 to infinity, not including the 0. And its range will reflect the domain of the natural exponential function. The range of this logarithm function, just like every logarithm function that we've seen, will be negative infinity to infinity. This function has no y-intercept, since, as we saw in 6.2, the logarithm with a base of e is the inverse of the exponential function with a base of e. The old exponential function had no x-intercept, and that is why our inverse function, the natural log, has no y-intercept. Similarly, the exponential has a horizontal asymptote, so the logarithm has a vertical asymptote. And this will graphically manifest as our graph approaching the line x equals 0, the vertical line, that is the y-axis. Now, we also saw that the exponential function contained the point 1e, so the inverse function will contain the point e1. We can use that to help our graph exhibit exactly the right amount of curvature. So, we can go ahead and plot the graph of this function as well. And I'll keep our graph of e to the x on here for comparison. E to the x, remember, looked like our exponentials, horizontal asymptote along the x-axis. Our logarithm function will have the x-intercept we discussed, a vertical asymptote along the y-axis. It will pass through the point e, 1, so about 12.7 and a height of 1, and will be increasing over its whole domain. It's worth noting that even though the natural log is getting special treatment, we're spending a lot of time talking about this particular base e, that this logarithm behaves exactly like any other logarithm function. Particularly, the properties of logarithms still apply. Namely, if my argument is 1, if I ask what power should e be raised to give me 1, we know the answer would be 0. If the base of the logarithm matches the argument inside the logarithm, then we just get 1. In other words, if I were to interpret the left-hand side of this as saying, what power must e be raised to, remember our base of e, in order to get e, I would conclude the answer would be 1. Similarly to rules 3 and 4, the natural log of e to some power yields the power. And if I raise e to the natural log of some x value, I would just get back the x value. And remember, x must be positive in order to be plugged into the log. So this rule number 4 is only true for positive values of x. So now that we know what the graph of both of these functions look like, we can transform them, just as we have with other less interesting logarithms and exponential functions. For example, if I wanted to graph the function f of x equals negative e to the x plus 2, you can see here the plus 2 is in the exponent, what transformations are we seeing? Well, where I usually have an x, I have x plus 2. This will correspond to a horizontal shift. Since it's inside the function, we are going to shift left 2 units. And outside of the whole function, we have this negative sign. The negative outside is going to manifest as a vertical flip. In other words, we'll take the function and flip it across the x-axis. So, if we were to graph our original function, here our basic function being e to the x, taking some points that we know, and I'm going to extend my scale just a little so we can see how all of these pieces move around. So we had the points 0, 1, and 1e. So my basic function given there. Now recall the order that we want to do these transformations in. My shifting always comes last. I want to do the vertical flip first, and then the shift. Now, you wouldn't be in any trouble if you did them in the other order, but you want to watch out for that if we are looking at the same type of transformations. So if I flip my function down across the x-axis, label our axes, looks something like that. And finally, shifting it 2 units to the left, each of those points can move over 2 units, and my function, make our asymptote work, would look something like this. We can do something similar by graphing the transformation of a natural log function. Now this one has quite a bit going on. Reading from left to right, I notice a 2 that I would not normally have, a negative factor multiplying x, the inputs, and a minus 5 tacked onto the end of the function. Now that 2 is multiplying our basic function, the natural log, so this would reflect as a stretch by a factor of 2. Our negative inside the function, multiplying x, would manifest as a horizontal flip. In other words, we will flip that function across the y-axis. And finally, we'll shift the whole thing down 5 units. I will graph each of those steps individually. My original function that we want to base all of this off of is the natural log. So if I plot those 2 points that I know, 1, 0 and E1, along with the vertical asymptote going down and the logarithmic growth going off as x increases, then I can stretch this by a factor of 2. I can pull that point, the x-intercept, multiplying its y-coordinate by 2 does not have much of an effect. Remember, our x-intercepts, if we stretch them, don't really go anywhere. But our y-intercept, our other point, E1, is going to get stretched up to E2. Right about there. So there's our stretch taken care of. Then we want to flip this thing horizontally. So all of these points that we know will be reflected across the y-axis, mirrored onto the other side horizontally. So 1, 0 is going to become negative 1, 0, and E2 will reflect across to negative E2. And finally, I would like to move the whole graph from part 3 down 5 units. Give myself lots of room. So 1, 0, which got shifted to negative 1, 0, is now going to get shifted down 5 units to negative 1, negative 5. Our second point, negative E2, will be shifted down to negative E2 minus 5 will bring us down to negative 3. Now I still need to asymptotically approach the y-axis, this time from the left, and my function will increase, eventually crossing the x-axis. We can in fact find the x-intercept. Remember, to find an x-intercept, we let y, or our function value, be 0. So if I set my function to times the ln of negative x minus 5 equal to 0, we'll see in the next section how to solve this type of problem. I'll give you guys a little preview. The way that I would handle this is I would first isolate the logarithm. So if I add 5 to both sides and divide by 2, then I'll be able to extract what is inside of the logarithm by converting this to an exponential equation. Remember, my base is e. The logarithm is equal to the exponent. And the argument of the logarithm is the result of raising e to that exponent. At this point, I have a little bit more work to do. I have to multiply or divide both sides by -1 in order to find x. So I see that x is negative e to the 5/2, which we could evaluate in the calculator. If I raise e to the 5/2 and take the negative, I find this is approximately negative 12.182. So we'll see more of that type of thing later on in the chapter. In previous sections, particularly 6.1, we saw the exponential growth model, or decay, if our base was less than 1. We can form an exponential growth or decay model using the natural base as well. And its structure is very familiar. We would say the amount, the population, if you will, with respect to time, is the initial amount times the base e to the product kt, where p sub 0 is, as before, the initial amount, initial quantity, e to the kt acts as our base. Now this number k is called the continuous growth or decay rate. And that is distinct from the base. Now, using laws of exponents, I could interpret this function using the power to a power rule as p sub 0 e to the k to the t. And here we see that e to the k is standing in for our usual b. So e to the k represents our growth or decay factor. Recall that growth and decay rates or percent increases are usually given as percentages, but for our purposes we need this value k to be expressed as a decimal. Before we can do any calculations. So an example of this type of function might be a, let's say, a dollar amount function. So the amount of money after time t, where time can be measured in any quantity we want, days, weeks, months, years, is 250 e to the negative 0.024 t. So identifying the pieces is as simple as picking out their location in the function. Our initial amount would be the amount that we would calculate if we allowed t to be 0. But we don't need to do that much work. We know whenever we do that the exponential portion of our function becomes 1, and we just get the constant multiplier out front. Our continuous growth rate or I should say continuous growth or decay rate, we're not sure which one we're dealing with yet, is simply the value of k, negative 0.024. We could rewrite this function, a of t, as 250 e to the negative 0.024 to the t. And in this form, it would be a little bit easier for us to interpret whether or not this function represented a growth model or a decay model. We can do this by examining this quantity, e to the negative 0.024, to determine whether it's greater than 1 or between 0 and 1. In my calculator, this number evaluates to approximately 0.9762857. In other words, our base for this exponential function is less than 1. It happens to be greater than 0, it always will be, but what I take away from this is that this is a decay model. This function will be decreasing. So our continuous growth or decay rate is a decay rate. And our decay factor is that value, e to the negative 0.024. So that is all of our new concepts. Go ahead and get started on the homework problems for this section and bring any questions you have to class.